Hello and welcome to another instance of Learning with Charlie Life. Today we're going to talk about the interval estimation. In the case we have sigma known and sigma unknown. So,
Today we're going to be talking about interval estimation, and when we're doing interval estimation, we have two cases. One is the one that has sigma as known, and this is the one that we call sigma as known, and then the other one is the one that where sigma is unknown. This is the one where we call sigma is unknown. So what we are trying to do with all of this is that we're trying to get an estimation of the true expected value uh, or the true population parameter. However, the the exact value is unknown. What we're going to do is we're going to use a point estimator, and we learned that x bar is a good estimator for mu. So in both situations, sigma known or an unknown, we're going to try to get an interval estimation uh, that is going to give us some sort of confidence that the true population parameter is in that interval. So normally what we're gonna do is we're gonna get a point estimate, um, and then we're gonna add or subtract plus or minus margin of error, and we're gonna call this margin of error. And the idea is that we need to get some sort of way in which we're gonna estimate the margin of error. So the purpose of an interval estimation is to provide information about how close the point estimate is to the true value of the population parameter. So to put this in perspective, if mu is let's say we have a normal distribution where mu is the center of the distribution. Let's call this the center of the distribution, mu. And then we take a sample, and then with that sample we get an x bar, an estimation of mu. So of course x bar is not necessarily mu, but it's close, let's say. So we're gonna get a point, and that point is going to be called x bar. And we would like to have a situation where x bar is very close to mu. So we would like that with some probability, we would like that x bar is very close to mu. And that's where we're gonna use probability, and then we're gonna try to figure out the margin of error. This is the margin of error. And we would like to have mu we would like to have x bar very close to mu within a margin of error, okay? Another way to write this would be something where we actually write down the probability. So the distance between x bar and mu, we can write that down as using the following expression. So the distance between x bar and mu is just the absolute value of the difference between x bar and mu, and we would like that to be smaller or equal than a certain margin of error, right? And because this is a probability distribution, then we would like the probability of this situation to be equal to a certain number, and we can call this, for example, 95%. So we would like to have some probability that the distance between x bar and mu is smaller than certain margin of error, okay? Now in order to actually get all of this, we need to understand what is the sampling distribution of x bar, and that is something that we know. We learned that the sampling distribution of x bar is such that we have a normal distribution with a parameter mu, and parameter sigma x bar, where sigma x bar it's going to be equal to sigma divided by the square root of n if we know the value of sigma. So this specific case is for the situation where sigma is known. So if sigma is known, then we know the specific distribution, and then also we know that 95% of the time the values will be within 1.86 standard deviations. So we can actually rely on that information to say that somehow if we have the situation where we have the normal distribution and the normal distribution has center at mu, then with 1.96 standard deviations, or also that the margin of error equals this is the margin of error equals 1.96 standard deviations, so sigma x bar. So if we have that situation, then we will be confident that 95% of the times x bar will be within that range. Okay, so given that, then we can generalize this idea. This is for the specific situation where we want to target 95% of probability, right? Now, if we are targeting 95% of probability, that means that we're leaving outside 5% of the probability, or if you can think of this as 5% divided by 2 on the lower tail, and then 5% divided by 2 on the upper tail. All right? So if instead of having 95% of probability or confidence, we want to have, I don't know, 99% of probability, then we need to have 1% divided by 2 on the lower tail and 1% divided by 2 on the upper tail. All right? So we can actually generalize this concept. If we know sigma, then we can actually think of the normal distribution. The normal distribution is like this, and then we have mu, which is the center, and then let's say we want to have 1 minus alpha confidence, meaning that we would like to have alpha halves on the lower tail, and then also alpha halves on the upper tail. Okay, that's important, because that's gonna give us a way in which we can actually determine the estimation of mu of the confidence interval if sigma is known, or the estimation of the confidence interval. So if that is the case, then we know that we will have z alpha halves on the upper side of the distribution, and then negative c alpha halves on the lower tail of the distribution. And because of that, we know then that the interval estimation of mu would be x bar plus or minus the c alpha halves times the standard deviation of x bar, which is sigma over square root of n. This is a very special case. This is the case when sigma is known. So this is good, sigma known. Now the situation, it's a little bit different if we don't know sigma. So what happens if sigma is unknown? So if sigma is unknown, when we need to estimate sigma. The best way to estimate sigma, if we don't know sigma, is use a point estimate for sigma. The best point estimate for sigma is what we call S, right? So if we don't know sigma, we're going to use an estimator for sigma. That one is called S. However, when we use S, we're incurring in some sort of estimation error. So because we're getting some estimation error, then we need to modify the distribution. We're not going to be using the Z table. Now we're going to start using the t-distribution, not the normal distribution, but the t-distribution. And the t-distribution, it's a very special distribution. The t-distribution is a family of distributions, actually, that will depend on not only the probability but also the degrees of freedom. So for this particular case, we need to know alpha, the significance, or the 1 minus alpha, which is the confidence. But also, we need to know the degrees of freedom. So, degrees of freedom are related to the number of observations. And the numbers of observations, it's going to be n. And because we're doing one estimation of one parameter, which is s, we're losing 1 degree of freedom. So then degrees of freedom are going to be the number of observations minus 1. Okay? So if n goes to infinity, then we have that the t distribution goes to the c distribution, all right? But if the number of observations is not infinity, and normally we don't have infinite number of observations, then we need to make sure that we're using the correct t distribution. So if that is the case, and we don't know sigma, and we're using an estimation of sigma using the parameter s, the sample s, then we're going to have a very similar confidence interval, but now instead of having the z, we're going to have the t. So the confidence interval is going to be x bar plus or minus t alpha halves times s divided by square root of n. All right. Again, the important points here are that the margin of error would be this expression, margin of error, which is t alpha halves times s divided by square root of n in the case of sigma unknown. And the situation is such that we have the margin of error equals z alpha halves times sigma divided by square root of n as the margin of error when we know sigma. So that's it.
If you know sigma, then you use the regular normal distribution or the z-table. But when you don't know sigma, you're fancy, and then you use the t-table.